Hello, everyone, and welcome to the MIT IoT seminar series. It is my great pleasure today to introduce Dr. Ranveer Chandra from Microsoft. Ranveer is the CTO of Agri-Food. He is also the Managing Director of Research for Industry and Head of Networking Research at Microsoft. Ranveer's research has shipped in many Microsoft products. I'm sure that all of us have at some point worked with some product that Ranveer has contributed to, ranging from Xbox to Azure, Windows, and Visual Studio. In 2015, he started a very exciting project called FarmBeats at Microsoft. This created a lot of excitement in both the academic and the industrial community, and it shipped as a Microsoft product in 2019. Bill Gates featured his work in Gates Notes, and as a result of this project, Ranveer has been invited to present the work for the Secretary of Agriculture, as well as to the FCC chairman. He's also a highly prolific researcher, has published over 90 research papers, has over 100 patents that have already been issued. And he's received many Best Paper Awards. He's been recognized as an IEEE Fellow. And he was also named as one of the world's top 35 innovators under 35 by MIT Technology Review in 2010. Without further ado, it is my great pleasure to handle the screen over to Ranveer.
Thank you, Father.
Take it away. Thank you.
Yeah, thank you for the wonderful introduction. It's wonderful to be here to talk to all of you about some of the work we've been doing in the agriculture space. The other thing I did want to mention before I start is that I also lead the networking research group at Microsoft. I started in this group at Microsoft Research right after my PhD, and I came back, and we are solving a lot of very, very cool problems there. So there are a lot of opportunities, even in the networking space, where I would love to talk to you. So today, let me start talking about agriculture and some of the work we're doing in that space. So before I start, I did want to mention that my background is not in agriculture. I'm a PhD in computer science. I did growing up, I did spend a lot of time in farms. I grew up in India, and in India, I used to spend a lot of time. As it happens, I see some people from India on the call. And when you grow up, you spend a lot of time with your grandparents. So I did too. I used to go to this village in North Bihar. Bihar is one of the states in India, in the south, to spend a summer and winter vacation with my grandparents. Back then, I did not like anything to do with agriculture. These farms were in the middle of nowhere. To get there, you had to take a train, bus, and then you had to get in a horse cart and get there. It used to be quite an expedition. And these villages, they did not have any electricity. They did not have any toilets. And that is how I used to spend 3 to 4 months every year. But that said, during that time, it did expose me to a lot of poverty, a lot of very primitive forms of agriculture, like hand-based seeding, bullock-driven tractors, and so on. And that led to the start of this particular project, FarmBeats, in 2015. I had been thinking about it for a while, and that's when I started this project. So the goal of FarmBeats is actually, the goal of this project is much more. That is, as many of you know, the world has a food problem. The world needs more food compared to recent levels. It's 50% more food by 2050 to feed the growing population of the world. It is not just about growing food, it's about growing good food, giving nutritious food to the people. And to do this without harming the planet. The amount of arable land is not going up, the soils are not getting any richer, the water levels are receding. So given all of this, how do we address the problem of sustainably nourishing the future population of the world? And as you know, as I just mentioned, these are just some numbers to put these statistics in perspective. We need 70% more food compared to 2010 levels. And more than 2 billion people, that is, we are talking of close to 25% of the world, don't have good nourishment. And many of these farmers are smallholder farmers, and many of them are suffering from hunger as well. One of the most promising approaches to address this problem is that of data-driven agriculture. What we mean by data-driven agriculture, for example, if you could map every farm in the world, like what you're seeing here, and overlay this with data. This is just one example. Like, for example, what is the soil moisture level 6 inches below the soil throughout the farm? What's the soil nutrient level? What's the soil pH level? If you could build maps like this, it would enable techniques like precision agriculture. That is, if you had a map like this, a farmer could apply water where it is needed, pesticide only where it is needed. And precision agriculture has been shown to improve yields. You can take care of plants better. It has been shown to reduce cost because you use less water, less pesticide. It is also better for the environment for the same reasons. You're not wasting water, you're not wasting pesticide. And in fact, it's not just about the farm. If you look at the entire agri-food system, all the way from inputs to tractor companies to a farmer, to how this, to post-harvest as well, to the food processors, to the distributors, retailers, and the customers, every entity in the food supply chain would benefit from capturing data and using that data to drive their insights, to improve efficiencies. In fact, if you could start sharing the data across the entire supply chain, it could unlock even new efficiencies and new business models. And these are just a few examples that I've listed here. For example, one of the things people talk about is food safety. That is, how do you know, using track and trace scenarios, if you could start enabling a retailer or a customer to know how was the food grown, how did it come all the way from the farm, through the warehouse, through the food processors, to the retail store, to the consumer, it could then enable food safety as one of the applications. Sustainability is again picking up as another application. Precision agriculture is another one. For example, there are recent discussions going on in DC around how do you can you incentivize farmers? Can you pay farmers for using the right agricultural practices? Of course, to do that, the farmers need to share information about what's happening in the farm. Input companies need to share information about what their seeds and chemicals are. Digital tool providers need to share information as well. So this is the future. We all know that agriculture and a food supply chain would benefit from data and data-driven agriculture. However, the adoption of these digital agriculture techniques have been severely limited. And the key reason these technologies haven't taken off is the cost of existing data-driven agriculture solutions. It's just very expensive to deploy any of these digital solutions in remote areas. There is very little return of investment for deploying any of these solutions, either throughout the food supply chain. So at Microsoft, we've been addressing some of these challenges over the last 4 or 5 years, and I'll talk about a few of these things that we've done, and later on towards the end of the talk, touch upon some of the open problems in this space. So one of the key reasons existing solutions haven't been adopted is the lack of connectivity. That is, the farmer's house has some sort of connectivity to the cloud. Most of these farmers' houses have point-to-point connectivity, for example, using wireless technologies. And they pay for broadband, they get like 1 to 3 megabits per second connection. But the actual farm is a few miles away. Even though connectivity might sometimes exist when you plant the seeds, by the time the crops grow, the connectivity is gone. So then the question is, how will you get data from the middle of the farm to the farmer's house? That is not just data from sensors, data from tractors, data from drones, data from cameras. All of this, how will you send data from the middle of the farm to the farmer's house when there is little or no connectivity? At Microsoft, we have been looking at various approaches to address this problem. I'll talk about one, but we're also looking at things like space communications. There's some new efforts we are doing around space. We're also looking at new ways to use, say, private 5G networks. One of the other innovative ways we've been looking to solve this problem, and something I have been personally working on since 2005, is a technology called TV white spaces. What the TV white spaces enables is, imagine if you have a Wi-Fi router that you could access miles away, right? Like that would be cool, right? Right now, as soon as you exit your house or your building, the Wi-Fi disappears. The way we achieved this was we took a Wi-Fi signal and we put them in an empty TV channel. This is TV you watch using over-the-air antennas. You know, when you browse through TV, on certain channels, you get a transmission. On the other channels, all you see is white noise, nothing coming there. The technology we had built was a way to take a Wi-Fi signal and put it in these noisy TV channels in a way that doesn't interfere with your TV reception in an adjacent channel. And the reason this is so cool is that compared to Wi-Fi at the same power level, In UHF TV channels, your signals go 4 times farther. In VHF, they go 12 times farther. And this is in free space. Once you put in trees, crops, canopies, your signals just keep going through. So this was a technology we had built back in the day. Into 2010. The FCC chairman had come to the Microsoft campus to see the demo we had put together, and this was made legal in the US in 2010. Since then, we've gone outside, deployed this technology in rural areas throughout the world, connecting hospitals, high schools, dispensaries, libraries to the internet using this technology. In fact, actually, I'll finish this one. In 2017, Microsoft announced an initiative called the Airband Initiative, through which we've made a pledge to connect 3 million rural Americans to broadband by 2022. And this is one of the key enabling technologies using which we are getting there. One of the key insights for agriculture was that TV towers are where people are. You have TV towers in cities. You have TV towers in Boston, in Seattle. The farms are typically away from the cities. So if you turn on a TV in the middle of a farm, most of the channels are just white noise. Even if 20 TV channels are available, each TV channel in the US is 6 megahertz wide, we are talking of 120 megahertz of available spectrum in the middle of a farm. And here I'm being conservative. I was giving this talk at the National Corn Growers Association. There was a lady farmer from Kansas. She lifted her hand. She said, we only get 2 TV channels where we are. Most of the channels are just available. So there's huge amounts of available capacity in the middle of a farm to provide this kind of connectivity. One other thing we did here very recently was we've created an IoT radio to operate in this spectrum as well. We've worked with the FCC, and most recently the FCC, this was in October, November last year, they passed new regulations around this, allowing these IoT radios to start operating in this spectrum as well, using which you can see how you could have many of these radios. If you have 6 megahertz channel chunks, each radio could be operating in 100 kilohertz of the spectrum. So you could pack large number of these IoT radios in the spectrum. The interesting thing is you now have VHF spectrum between 170 megahertz and 220 megahertz, giving you really long range in this part of the spectrum. We are using this technology to connect farms. So there's this farmer in Eastern Washington where he's getting over 15 to 20 miles of coverage in his farm, where he puts this base station in his house, and then miles around it gets connected, either for broadband or for IoT radios. The other challenge that we had to address was that of sparse sensor deployments. That is, I talked about these kind of maps. That is, what is the soil moisture map, 6 inches below the soil throughout the farm. If you had to build an accurate map like this, you would need lots and lots of radios. Like, for example, for soil moisture, you would need a sensor every 10 meters because, soil moisture varies from row to row. Or very recently, soil carbon is a hot problem. Many people are looking at that. Soil carbon is known to vary a lot in the same farm. However, putting a sensor every 10 meters is going to be expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the question we asked is the question you're seeing in the last bullet here. Can we build a map like this using very few sensors? To address this problem, our key idea was to use drones. These are UAVs, which have a camera at the bottom. They can cover large areas very quickly. And what we built was an AI algorithm to use sparse sensors and the aerial imagery, and use the aerial imagery to interpolate this data in different parts of the farm. In fact, that part of the algorithm was developed by an ex-MIT grad, Deepak, who's right now at Microsoft and then going to join University of Illinois. So the way the system works is we take aerial imagery, say from drones or satellites, or the other technique we built was using helium-filled balloons. That is, when we are talking of getting an aerial imagery of a farm, you could use drones, but drones are expensive to use in the emerging markets if you go to India or sub-Saharan Africa. So then the question is, how can you build and get an aerial image of a farm at very low price? So our idea there was to use helium-filled balloons, and these are tethered to the ground. What we built was a weatherproof mount where a farmer could put their smartphone with the camera facing down with a battery pack attached to it. And this thing could stay up from 4 to 7 days taking images of the same part of the farm. In fact, if you read Gates' Notes blog, Bill Gates, you can see him walking with this balloon in the farm, and we were showing how you could use it to do very low cost do very low-cost imaging, aerial imaging of the farm. In fact, his suggestion was kind of funny too. He was like, well, instead of helium, you could start looking at methane because, with these cows, they emit a lot of methane. His point was, can you actually reuse that methane to power these balloons and use that to do imaging of the farm? So now going back to, okay, once you get the aerial image, we use computer vision techniques to create these panoramic overviews, these kind of ortho mosaics of the farm. Then we take the place where you have sensors. We use wherever you have sensors, you have the ground truth data, you have the aerial imagery for that location as well. We use that to train a machine learning model and then use that machine learning model to predict these values in other parts of the farm where you do not have sensors. And using this, we showed that you could build these maps which are 3 times more accurate than existing schemes that do not use aerial imagery. The state of the art in building these soil moisture or soil nutrient maps is the Kregging method. You'll have experts either go take samples from the soil, or you have people who put sensors, and then you just use, say, a Gaussian method to interpolate this data as if it was a straight line, or just without using any aerial imagery. With aerial imagery, you get other surrogate parameters using which you can get up to 3 times more accurate maps for building, and we've used this to build maps for soil moisture, soil temperature, soil pH. Right now, we are using it for soil carbon as well as for methane as well. Of course, one of the challenges that we ran into when we were looking at aerial imagery was, you could use drones and balloons, but you won't get coverage. It's hard to see adoption throughout very quickly, at least for the next 10 years. So then the question was, how do you get aerial imagery if you don't have drones or balloons? Well, you could use satellite data. But one of the challenges of satellite imagery is that at any instant in time, more than 70% of the Earth is covered by clouds. If they are covered by clouds, you're not really seeing anything, what's happening below the clouds. So this work was done again by one of my other interns, again from MIT, Mingmin. He's in the job market this year. He built this thing where what we're combining here is data from another satellite, which has radar in it. The radar signals, as you know, penetrate clouds and they reflect differently from different surfaces. They reflect differently when the soil is moist versus when the soil is dry. We then use that along with another neural attention scheme to start seeing through the clouds, and using which we are able to construct daily imagery of what's happening below the clouds. Here on the left is what you're seeing existing satellite systems give you. On the right is what SpaceI can predict. It can predict how this farm is changing, even though right now what you would see is just cloudy images. We've used this for many other scenarios as well. Even when the last summer was very cloudy, we could see how the Microsoft construction site was coming up. We've used this to monitor forest fires, see forest hurricane damage, and many other applications as well. So I talked about how with the TV white spaces, you can reduce the cost of connectivity, and using AI, you can start combining aerial imagery with ground sensor data to create these maps at much lower price point. You need much fewer sensors than what you would otherwise need to start building these maps of farms. The third challenge we had to address was that of connectivity to the cloud. We talked about how using the TV white spaces, you could send large amounts of data to the farmer's house, or using things like private 5G kind of networks. But the connectivity from the farmer's house to the cloud is weak. Many farmers, they pay for broadband, but all they get is 1 to 3 megabits per second connectivity. Some of the, there's a farm in upstate New York, actually, it's very close to Boston. Every time there is a snowstorm, there's a high likelihood that his internet connection will go off. So then the question is, if we are capturing large amounts of data from the farm and sending it to the farmer's house, but we can't really send it to the cloud, how can we get benefits of all of this data to the farmer? Just to put this in perspective, every time you fly a drone, you could be getting gigabytes of data in a 15-minute flight. And if you have, say, 1 to 3 megabits per second intermittent connectivity, you can't really rely on sending all of this data to the cloud. Our key insight was that most farmers have a PC. If they don't have a PC, we ship them a PC form factor device that they can keep in the farm. And that PC can do a lot of compute sitting in the farmer's house or office. It can then send summaries to the cloud, where we then integrate with other data sources, for example, using satellite data, weather data, and so on. Just double-clicking on what's on the edge device, this computer sitting in the farmer's house, Everything you're seeing in this big gray box is what's running in that edge PC. It gets data from sensors, it gets data from drones where we do computer vision to generate panoramas. We then combine that with sensor data to create these heat maps, which then flow into these agricultural services, the ones you're seeing on the far right. These are services that we are not building. We are working with the experts to build these services. We also get data from cameras and others using TV white spaces where you could be doing deep learning at the edge. And I'll show one scenario where we are doing that. All of this data is lazily synced with the cloud. We also have unique storage that sits on the edge device. Not all the data needs to be sent right away. We prioritize what gets sent. And in some cases, large amounts of data would just be shipped, while parts of the more important parts of the data are immediately sent to the cloud. Furthermore, because this PC can be offline, we have web server that's running there to provide offline access. And there's some unique apps that only run on the edge and not in the cloud. So there are many other things in FarmBeats. It's been going on for 5 years, 6 years now, and we have many people who've contributed many things. You could go to the FarmBeats website and see the amount of research we did. I'll just talk about a few use cases of how different farmers have been using it. We deployed in farms all the way from 0.5 acre to 9,000 acres. And these are just some of the use cases. One of the things we do is when a farmer puts a sensor in the soil, we not only tell the farmer what the sensor values are right now, but we predict up to 5 days in advance what those values are going to be on an hourly basis. Here, what you're seeing is for soil moisture and soil temperature. The way we build these models is we took weather station data from 50 different weather stations across Washington state over the last 7 years at 15-minute intervals. We use that to then train a model. And when you put a sensor, we then do transfer learning to start making very hyper-local predictions for that particular sensor in the farm. And there's more to it, and I'm happy to share the paper with anyone who's interested. But we did this for soil moisture, soil temperature, wind, ambient temperature, and a few other parameters as well. And you can read more results in the paper, but in the bottom left of the slide, this is a testimonial by a farmer. This is a farmer who lives in Eastern Washington. He farms 9,000 acres of wheat. And here in this case, what he was looking to do was he was looking to apply chemicals in the farm. This is herbicide to kill weeds in a particular section of the farm. He looked at the weather forecast. The weather forecast tells you weather at the weather station, not really what's happening in the farm. The weather forecast said that it was going to be 42 degrees in his farm. But what we predicted was it was 31. It was actually 30 degrees. It was good. He didn't go and spray chemicals because it was below freezing, and he would have lost his crop if we went and applied chemicals that day. In fact, just going back to the previous slide, this farmer, every time he takes off his tractor, so just to talk about this farmer, he farms 9,000 acres spread across 45 miles. So every time he takes out his tractor, he goes and uses his tractor in different parts of his farm. Right now, what he also uses this technique for is to look at wind. That is, when he's taking his tractor out for spraying, he look at the predicted wind forecast throughout the day to make sure that the chemicals actually get sprayed in the areas he intends to spray it on. This is another use case we like talking about. This is a farm in upstate New York. This is a 4-kilometer stretch. The farmer wanted to know how his cows were doing once they are out in pasture. So we flew the drone. We transmitted the data over the white spaces to an edge device. And within 30 minutes, we were able to flag things like from left to right, the grass is growing back well. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which was also important information for the farmer. He wanted to know, because he wants this poop to be sprayed evenly throughout the farm. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is a farm close to Microsoft campus. We do a lot of demos here. This is the farm where Bill Gates spent a few hours. We had Satya here. We have several CEOs of agricultural companies who we've hosted in this farm as well. This is a smallholder farmer. He sells his produce in the farmer's market, and he used to sell it to restaurants when the restaurants were open. And here we were able to show this farmer these beautiful pictures, and we were able to overlay this with data. For example, this is a soil moisture map. We were able to flag that the bottom left bottom right parts of the farm are still moist, even though we did not have a sensor over there. This is a soil pH map. After the farmer had applied lime, we are able to flag that these dark parts of the farm are still acidic, and the farmer needs to reapply lime before planting the seeds. This is a deep learning scenario where this is the farm in upstate New York, where we have 3 barns with cameras where we're able to see how the cows are moving, whether a cow is sick, and so on, and flag that information to the farmer. The last scenario, for example, you can think of it like a baby monitor for cows, right? You can see how the cows are moving. The interesting thing there is you really can't be sending all of this information to the cloud because, well, this will just take up a huge amount of bandwidth, and it's just the ROI is not there. So you need some of the technologies that we talked about, AI, edge compute, connectivity in the farm, to light up those kind of scenarios, which are high value for the farmers that we work with. So this was all in research. We, of course, did a lot more. We were building everything end to end. But then in 2018, I'd moved over to the product side in Azure, and we announced our first product, Azure FarmBeats. This was announced in 2019 in November. So in particular, what we looked at was we saw all the existing ag tech solutions. There are many ag tech companies out there building their ag tech solutions. They get data from different types of inputs, and they write their own data ingestion, their own data store. They try to do analytics and create applications on top. And no single ag tech solution covers all of these inputs. And it's very bespoke, very broken. They have all the problems that we discussed about connectivity, about edge. Instead, what we did with FarmBeats was we took some of the common components used by these ag tech companies and then started bringing our innovations to that. Not all the innovations that I talked about are in the product yet. Some of them are, and we are working on bringing all the others as well. So the way we built it was we then work with multiple partner companies, sensor companies, drone companies. These are all partners of ours. We provide the APIs to them. We work with them, with some of them, to provide the TV white spaces capability, to provide the edge capability. We then have APIs using which all of this data is ingested in the cloud, where we then do the AI, build these AI templates for the ISV and partners to start bringing their solutions on top of it. So we're partnering with multiple companies, like, for example, DTN for weather, for satellites, it's with Sentinel. We are able to get John Deere data to the cloud. We work on sensors with Davis Instruments, with Pessl Instruments, and many others. And then we're working with ISV and partner solutions to light up the ag tech solution. So if you think of FarmBeats as a cloud platform using which we have data partners. These data partners can bridge their data, can bring their data to the cloud. We enable large-scale AI on top of it, but our go-to-market is through ISVs and partners. That is, we are not providing a farmer-facing solution at Microsoft. We are not an agriculture company, but we work with other companies that know more about agriculture. They are the ones who build their solutions and take it to the farmers. And these are just some of the companies that we've announced partnerships with, and there are many more that are coming down the line. Just to talk about a few partnerships over the last year, we've announced partnerships with Lando Lakes, with PepsiCo, with USDARS, and many more companies, including CSIRO in Australia, and the list, you'll hear about more announcements as well. I'll talk about one of them with Lando Lakes. This is Lando Lakes, as you know, is one of the biggest farmer-owned cooperatives in the United States. Lando Lakes announced in last summer that they are building their ag tech solutions on top of FarmBeats. And as part of that, they're bringing their key solutions like R7, all the Winfield solutions, and building them on top of the FarmBeats platform. We're also working with Lando Lakes on bridging the rural connectivity divide, where I talked about FarmBeats as TV white spaces as one of the approaches, but we are closely partnering with Lando Lakes on that as well, on how do you bridge the broadband divide. And we're also working with them on sustainability as to how do you put in more carbon back in soil, working with the Lando Lakes farmers. So in addition to research and taking things to product, we are also working on societal impact, taking some of the solutions to create real impact with the farmers. I briefly touched upon rural broadband as part of the Airband initiative. As you know, in the US right now, there are more than 23 million rural households that do not have broadband connectivity. In fact, the situation is much worse if you look at connectivity in the middle of a farm. There was a recent stat that said that only 25% of US farmland has any connectivity in them. So then the question is, how do you connect households and how do you connect the farmlands so that you can drive all of these digital agriculture solutions? As part of the Airband initiative, we are investing in this, and we are looking at TV white spaces. Along with other fiber solutions, we are creating partnerships with rural ISPs to bridge this rural broadband gap. One of the other key announcements Microsoft made over the last year was around sustainability. We made announcements around carbon, climate change, water, waste, and ecosystems. In particular, around carbon, one of the bold announcements Microsoft made, we were among the first to make this announcement, was we've pledged to be carbon negative by 2030. What this means is that we are going to be putting back more carbon than we generate by 2030. And by 2050, we've pledged to remove all the carbon emissions that we've ever generated since the time Microsoft was founded. And our CFO is putting in $1 billion towards a climate innovation fund to help us get there. As you can see, this is a huge, strong commitment. The question is, how do we get there? Part of how we get there is by reducing our own emissions. As you see in the blue line here, we are going to be reducing our own emissions, but that's not going to be enough. We have to invest in new ways, in new technologies to put carbon back in the soil, take it away from the atmosphere and put it back in the soil. So for people who are new here, just at a very high level, well, carbon above the ground is bad, carbon below the ground is good. And agriculture is one way in which you can put carbon back in soil. As you know, through photosynthesis, these things take carbon away from the atmosphere. They could be putting more and more of that carbon in soil. So farmers, if they use the right agricultural practices, they could be sequestering more carbon. For example, there are techniques which are now known as regenerative agriculture. If they practice technologies such as practices such as no-till or reduced till, or if they do cover cropping or other such smart agricultural practices, they could be putting back more carbon in soil. And right now, for us, for companies like Microsoft and other companies, this is a way in which we can meet our own carbon commitments. So in fact, last year we announced an RFP, one of its kind RFP, where we are looking at people to come to us to talk about, to submit the potential sale of carbon, that is carbon that we could buy. We did purchase carbon from 2 soil carbon sources as well, one from Lando Lakes. And this is more of an experiment. We realized that there are many unanswered questions around soil carbon. One of the unanswered questions here is, how do you even measure the amount of carbon that is sequestered in soil and measure it at a low cost? That is, right now, to measure the amount of soil carbon, you need people to go there and someone to monitor, or even if you have sensors and drones, all those sound cool, but they all add up to cost. How do you, in an economical way, measure the amount of carbon that is sequestered in soil? It's a hard problem, and we are investing. My team is looking at this here at Microsoft. We are also working with partners to address this. But for people working in this space, we'll be really excited to do partnerships in this space as well, to see how can we bring technology, how can we bring innovations to make soil carbon more feasible, both from a practice standpoint, that is, how do you enable farmers to adopt these practices, as well as from a market standpoint, how do you make the entire market take off by making these schemes more affordable and accurate. One of the other things we're looking at is rural skilling. That is, if you look at the rural community, one of the biggest, I was recently giving this talk at University of Illinois, and I was asked this question: what are one of the biggest bottlenecks that we face with adoption of digital agriculture? I think one of the bottlenecks we face is around the technology savviness of the rural population. The rural population is aging. A lot of the next generation of farmers these younger people don't want to be in farming. They'll go to the cities. So then the question is, how do we enable them to adopt any of the digital agriculture technologies that we're building? One of the things we did at Microsoft was we built a Farmbeat Student Kit. This was a kit where we worked with the teachers to create a curriculum around it as well. And we are giving it to the FFA's Future Farmers of America high school chapters, so that when the students are in high school, they can get to learn some of the latest on data, on AI, on machine learning, and how they could use this in their farming operations. We're also working closely with universities on different aspects of the supply chain. When COVID hit us, one of the questions that we all faced was, what is the disruption being caused to the food supply chain? One of the work we did, what you're seeing on the right, is with the head of Ag Econ at Purdue University, Professor Jason Lusk, where we created a dashboard where you could go and click on a state and a commodity, and it would tell you what is the ag worker risk and the commodity risk for that particular commodity, be it vegetables, chicken, or anything else, in for different states across different counties as well. The thing you're seeing on the left, this was a dashboard we created, again, working with faculty at Purdue University to connect smallholder farmers to the customers. Because, during COVID, and these days I'm hearing a lot of that happening in India as well. I don't know how many of you are aware, but India is going through this real major spike of COVID. And as this happens, we think about the health of people. That's the number one thing that's top of our mind. But if you take it the next level, the entire food chain stands disrupted. If you look at farmers, they don't know where to sell their crop. A lot of the logistics companies are not operating. A lot of the cities are in lockdown. So what we did here was we created a virtual market, and instead of directly connecting farmers to consumers, we built this thing for farmer market makers, where these are the people who run farmer markets, who could then connect the farmers to the consumers, allowing them a channel to sell their produce. So of course, at Microsoft, we've been working on this for a while, and we have a huge ecosystem of partners using which we are working on getting this technology out to the agriculture stakeholders, to the farmers in the US and worldwide. That said, towards the end, I just wanted to conclude by talking about some of the open problems. Right now with FarmBeats, as you know, it started as a research project, it's shipping as a product, but I believe we are just scratching the surface in enabling digital agriculture solutions. A lot of open problems need to be addressed. I talked about one which was around sustainability, where a lot of we need to where I talked about some of the problems around enabling farmers to adopt it and reducing the cost of those solutions. The other thing we are looking at is, how do you bring these technologies to small scale producers? As you know, in the world, there are close to 500 million, 500 million plus smallholder farmers. And in particular, if you're looking at regions such as South Asia and India, Bangladesh, Pakistan, or if you're looking at sub-Saharan Africa, a lot of these farmers are small farmers. And there are some very unique challenges that come up when you think of these small farmers, because they have these small farms, they are in the same farm, they start planting multiple crops, up to 9 different crops. If you do that, you can see how it becomes very hard to use any of the solutions that I was talking about before. So what I did, this was work we did with the Gates Foundation. I wrote a paper that would be coming out in the communications of the ACM on some of the challenges and opportunities for smallholder farmers. What we did was we created this hype curve for all the technologies that we see and their applicability to smallholder farmers. And as you can see, there are a lot of these technologies that are near the trough of disillusionment. And the question was, what do we need to do to take them to the next level, to help them clear the bump and help them get to this area of maturity? So towards that, of course, one of the key challenges we need to do is reduce costs. So how do you make it more affordable? That's just one of the challenges. And there are many more things that you need to do, which I'll talk about in a little bit. Some of the work we are doing internally on how do you make the cost down. I'll talk about just as one of these technologies as an example, but we need to do a lot more. And I know some of the work happening at MIT, like the work that Fadil's done, is also super cool around food quality and things which all need to be part of these solutions. We need to get them out to make more of these digital solutions adopted in the emerging markets. One particular problem we looked at was around affordable sensing. So these sensors I talked about, these sensors for agriculture still cost a few hundred, like $500, if not more, per sensor. If you think of smallholder farmers, there is very little, they are not likely to buy a sensor which is a few $100s, even to measure things like soil moisture. And the biggest blocker there is they don't see the ROI. The sensor will give you one the measurement at one location, and they don't see the return of investment of spending a few $100s. It's way too expensive. So our idea then was, can we do it? Can farmers use their existing phones to start doing these measurements? That is, even though these farmers won't spend a few $100s, many of them have a phone, usually a smartphone, even if it is a very inexpensive smartphone. If they have a smartphone, it has a Wi-Fi chipset in it. If it has a Wi-Fi chipset in it, the key idea that we had was if you could measure the time of flight of Wi-Fi, it could then be used to estimate soil moisture and soil EC. Just based on physics, as you know, the time of flight of an electromagnetic signal depends on the permittivity of the material. So if you could somehow measure this time of flight, you could map it to things like soil moisture and soil EC. So we built a system where the key challenge though is, this time is of the order of nanoseconds, and you don't have enough of a bandwidth in Wi-Fi and 2.4 gigahertz to measure time in that resolution. So our key idea there was that, most of these Wi-Fi chipsets that are in smartphones have multiple antennas. So instead of measuring the absolute time of flight, it is more feasible to measure the relative time of flight. And we use that to create a system we called Strobe. We wrote a paper on this, which was published in ACM Mobicom. It got one of the awards at that conference as well. In fact, we demoed it to Bill Gates when he visited the farm. And the title of his blog was, "Can the Wi-Fi in your phone help feed the world?" So we are envisioning a future where any farmer can just use the existing phone, take it around in the farm, and they can map the farm. They can get the data from the farm to drive these data-driven agriculture solutions. In fact, last year, around this time, I was just before the lockdown, I was giving a keynote talk at the National Academies at one of the agriculture workshops that was organized there. And I was giving this talk, and one of the people in the audience was the World Food Prize winner last year, Dr. Ratan Lal. He's a professor at Ohio State. And the World Food Prize is like the Nobel Prize for Agriculture. And he got very excited with the results that we were showing him. He was like, well, if you can measure soil moisture, I can use it to measure as a proxy for soil carbon. So that's one of the things we are excited about as well. Can we really democratize sensing? Can we take these technologies to, say, the smallholder farmers in India or Africa who can just use their phone to start estimating the amount of soil carbon that's soil organic carbon content in soil? So actually the work we did with Stuart Collis at the Gates Foundation, this is, we wrote a paper which will be coming out soon, which will talk in more detail about each of these. We looked at all these technologies, the one you're seeing on the left, and we looked at all the hard problems that exist. Some of the 4 key problems we looked at because of which these systems haven't seen adoption. One is around affordability, that is, they're just expensive. The second is around relevant data, that is, it's hard to extract. We have large amounts of data, but we don't have the right labeled data from the farms to start generating value on top. The third challenge is around connectivity, around data platforms. How do you, most of these places don't have good internet access. And there's a very interesting problem around internet connectivity. Around 40% of the world doesn't have internet access, that they're just not connected to the internet. It's not because they don't have a wireless signal that they can connect to. The challenge is it's not affordable. And the other interesting thing we found out, which was around the gender disparity around connectivity. There are far more women in the world who are not connected than men. So these are all problems that we need to address as part of the connectivity challenge. And the fourth challenge was around usability. There's a big technology gap in the emerging markets. And how do you make any of these technologies more usable? So around that, these are the 4 columns. So we then mapped them to different computer science areas. If you look at it, hardware and architecture, SIG-ARCH, and vision is again the vision community, the SIGGRAPH community. The third column is around the SIGCOM, SIGOps community, and the fourth is SIGCHI and others. And we looked at some of the key hard problems that need to be addressed to make these systems adopted for any of these, to make them affordable and adoptable for the emerging markets. We also looked at the maturity of each of these technologies. The green ones are more mature. These are the ones that are more likely, more ready to take off. They're still not completely ready, but they're close to that. The ones in yellow are more advanced, but a lot more work needs to be done to make them adopted. And the red ones will require a lot of research. If you look at it, if you have to just look at what are the key takeaways from this, as you can see, sensors and satellites are more mature. There's more work happening in this space, and they are the first likely ones to take off. AI and machine learning, if you look at the second column, they can bring benefits to any of these techniques that are being used for digital agriculture. And of course, just to end on the opportunity here, robots and drones and automation, they're mostly in red. A lot more needs to be done if we need to get them to be adopted and usable for the smallholder farmers worldwide. So to conclude, that was my presentation about the opportunities that exist in digital agriculture. We've done quite a bit of work around FarmBeats. We are working with some of the biggest companies and some of the governments worldwide as well. But as I said before, we are just scratching the surface. There are a lot more problems that need to be addressed if we are to bring digital agriculture to farmers worldwide and help address the world's food problem. Thank you.
Wonderful. Thank you very much, Ranveer, for a very exciting talk. I've personally been following the work for many years. It's exciting to see it come so far, and the vision and what it has already transformed and what it has the potential to transform. So thank you for joining us today and sharing that with us. We have a few minutes for questions. If anyone wants to ask a question, either you can use the raise hand feature. For example, you can click on reactions and then, or you could write in chat, and if folks write in chat, I'll be able to relay them to Ranveer. So anyone who has questions, they can. Patrick, do you want to go? And I will allow folks to unmute themselves. Okay, you can unmute yourself now.
Great. Thank you for the talk. It was really interesting. So my background, at least the past few years, has been in like outdoor and indoor sensor deployments. And in my group, we have one project where we've deployed a bunch of physical sensors out in a marsh. They're a couple meters spaced apart, and we've been finding that the sensor readings between each node are quite different. Again, this isn't it's not a farm; it's a recovering marsh, so the topology is a bit different. But I'm curious on how accurate your interpolation techniques are, and you do say that you have some physical sensors on the space. So what density are we talking about? Like several meters to tens of meters, or what?
Yeah, this is a great question, Patrick. And right now, both these questions are different. So the first question is, I'll answer the second question first. How many sensors do you need? So to answer that question, we have a sensor placement algorithm, which looks at things like how heterogeneous is the farm, what is being planted, how heterogeneous has it been in the past. So we look at historical data. And based on that, we then use essentially the value of information algorithms to figure out what are the right places to put the sensor. One of the other variants of that we're looking at is, if you give X number of sensors, where should you put it, right? So we have an algorithm for that. So that's what we're using. The second thing was around accuracy. So we have ways in which we detect anomalies, that is, if something is not right, if some of these results are not accurate, we're able to flag that. But yeah, ideally we need these systems we rely on sensor accuracy. And that's one of the reasons existing sensors are so expensive. That is, the reason they are expensive is because they offer that kind of reliability. Like they are just so robust. They're using high-grade equipment so that to make sure that what you're getting is reliable data. That was one of the challenges which I think we need to address. How do we get sensors at that accuracy and that reliability at a price which is affordable for farmers?
Ranveer, if I also remember correctly, in the FarmBeats paper, you used spatial similarities between areas. I think what Patrick was saying, sometimes if two things are close, they might have different measurements. But I remember is that correct? Like by combining it with these aerial measurements, you can actually know that they're different because they.
Right, exactly. So that was the sensor interpolation algorithm, where what we do is, what Fadil is saying is exactly that. So if there are two parts of the farm which are different, they show up in the aerial imagery. When you're talking of aerial imagery, it's not just optical, not just RGB bands. We're also looking at multispectral and hyperspectral bands as well. So that would reflect things like, varying amount of carbon or varying amount of pH, are things that you can see in optical imagery. So that can again be used to flag that certain sensors might be misbehaving, or sensors might be inaccurate, or to even see places where you don't have sensors, how things are varying. Yeah, there was another interesting piece of work, Patrick, that we've done was around flagging when sensors fail, because what we realized is once you put sensors out in the farm, things can fail. So we published this paper in Census, where we're looking at the voltage curve. What this is if you have a sensor we apply a voltage and then we just take off the voltage. What happens with that? We just turn off the power source and then we monitor how the voltage goes down. It's not a sharp curve because the sensors are an RC circuit. So what you'll see is that there is a gradual degradation. If the sensor breaks or something's broken on the sensor, this RC curve changes. So we call it a fall curve, using which you can flag when things are breaking as well. So just a cute idea which we used.
Great. Isaac, you also had a question.
Yeah, thanks for the talk. It was very interesting. At the beginning, you mentioned kind of this idea of data along kind of the whole spectrum of farm to table. And I was wondering if you had any thoughts to add on kind of ways to integrate data more downstream, such as on the logistics or food waste side, once it gets past the farm.
Right. No, that's an interesting challenge too. How do you carry this data through? There's some very interesting startups that are coming up with these tags that you could attach to produce to carry this data through. There's of course all these blockchain scenarios people talk about, and there are a lot of interesting things happening in that space. Primarily driven by food security and traceability applications, where people are talking about this, but that's where more of this is coming through. But some of the hard problems still remain. One is, you don't get data about how the food was produced. All the data that is being carried through is post-harvest. Once you harvest something, you can carry the data, but you're not really carrying the data from the farm. That's an open gap right now. The other open gap is around food processing. That is, you got these sources, you got this food, this inputs from multiple sources, but then the food processing center, you're going to combine these things, say to create flour from wheat or other things, where once you do that, you're not really tracking how things happened or before the processing stage. That's again another open problem. And the third open problem, I think, which we encounter when talking to multiple companies, is around supply chain when things are coming from the emerging markets, things like you look at the spices market or the coffee market or others, where what's happening in the farm in these emerging markets. And primarily because a lot of these food companies want to market their product as sustainably sourced, sustainably on multiple dimensions around use of water, around child labor, around carbon and other practices. But it's very hard to infer those and carry that information through the food supply chain. So all I'm highlighting to you, Isaac, are the problems that exist. There are some innovations that are happening. People are talking about coming up with ways to infer if a food is safe or not. And there's using hyperspectral cameras. There's this new work we're looking at from Eastern UK using multispectral cameras. There's some interesting work going on, but I think there's so many more open problems to really light up the scenario that we're talking about. And yeah, if you have thoughts, we'd love to partner with you on those.
Thank you, Ranveer. We have quite a few questions more, so we'll try to sift through them. So Naveen asks that they're curious if there was any sign of digital hesitancy on the side of the farmers. Were they reluctant to have their data collected and or to trust ML AI algorithms? Yeah,
this is a very important problem. I usually get asked, who owns the data? Is Microsoft owning the data here? Right. So from our perspective, we are not owning the data for it because we are not the ones providing. We believe that, the way FarmBeats gets to a farmer is through someone else. That is, they might not even know that FarmBeats is used behind the scenes. So for us, it's an agreement between the digital advisory provider and the farmer. What we are doing at Microsoft is providing a way in which data can be shared securely and in a privacy-preserving way. But this is a very important problem. Who owns the data? The data shouldn't get in the hands of people who, in the hands of people who could use it in not a great way. The same image recognition algorithms that you can use to unlock your iPhone can be used by other people to track things that shouldn't be tracked. And even over here, we should make sure that the data doesn't fall in the hands of the actors who shouldn't be owning that data, shouldn't get access to that data. Which is where we are looking at some interesting ways to solve that problem using things like confidential compute or homomorphic encryption, where you're able to do AI on encrypted data. So you're able to share data to bring all the benefits of digital agriculture without actually getting access to the raw data. When I was with FarmBeats, though, interestingly, I didn't face that hesitation yet, but I get asked this question every time I talk about FarmBeats, and I think this is a very important problem.
Another question is, how do you power the ground embedded sensors?
Yeah, right now they're all battery powered, right? Which is we need to do more there. And there's some work with UW who's looking at using RF to power sensors, which I think is a very interesting idea because with TV white spaces, I talk about how you're putting an antenna in the farm, right? So once you have an antenna in the farm, you have an RF power source where you could even direct this power source if you have multiple antennas to the sensor to start charging them. This is still in research, but I'm bullish about ways in which you can charge it using other ways. And people also talk of using earth batteries, using the earth as a battery. I think that would be a cool thing to try out as well. They're interesting ideas, but right now from a product perspective, we still use batteries or solar panels, which again, power batteries, which power the sensors.
Great. So a couple of also related questions. One of them is, have you seen, are there pushes for FarmBeats to be applicable to regenerative agriculture practices instead of traditional ones? And one that is also related to it is, have you thought about aquaculture applications like fisheries or aquaculture? This was not a question from me, but it's a question that I would have wanted to ask, as you might
expect. I know. You do so much cool work in this.
Because actually the ideas are, you could use very similar ideas and apply them. And it's also one of the fastest growing markets, as you know.
No, aquaculture is huge. So the first one regarding regenerative agriculture, I think, that's something which the carbon work we are doing on top of FarmBeats is all around this. How do we encourage farmers to adopt more regenerative agriculture practices? Use things like no-till or reduced till. Use things like cover cropping, which cover crops to plant, how will the cover crops grow? How do you monetize cover crops? And those are things that we are actively looking at and trying to address. So that's definitely one of the next use cases of FarmBeats. The aquaculture one is very interesting, right? So there there is increased adoption of digital technologies for aquaculture, in particular for things like salmon and shrimp, where people are looking at these cameras and they look at these, using the cameras, they're trying to identify how the fish are moving and fish health and fish feed, because all of this goes into the fish feed market. What do you feed? When do you feed? To do precision feeding for the fish, and which is a huge market by itself. I think, and there's some new work there is around sound. That is, can you, like, instead of using all cameras, which don't always work that well, can you use sound to, like, you have an acoustic thing in the bottom of the water, which is then monitoring how the fish are moving. There's very interesting work there. Of course, those again are super expensive, where some of the work that Father you've done around communication in water, I think would be hugely applicable. I think there is a lot of scope. And that coupled with a terrestrial solution, that is, I think, because most of these things are offshore, which don't have great connectivity. So you get something from up there and use a low cost way. Right now, a lot of them use satellite connectivity, which quickly drives up the cost. Now, of course, who knows, in the future with LEO satellites, things could be different, but for now, they're still at a point where for a lot of these IoT applications, especially with uplink, they might not work. So all the components we discussed around connectivity, edge compute, or AI ML, all of those things are applicable and more. I think, but hugely important problem. I would love to work with you all to see what we can do there.
I'll just take a couple, actually just a couple more questions to be mindful of your time. So one is, Stephanie's asking, how will you solve for connectivity if TV white spaces get filled?
Yeah, no, so that's hopefully, so we would want it to get filled. The interesting thing is, in these remote areas, we're talking of remote areas. In cities, the TV white spaces are filled anyways. And it's outside the cities where it is not being used is where we want to use it. And TV white spaces relates to this bigger concept of dynamic spectrum access. That is, there are different parts of the spectrum which are not being used, and especially so in rural areas, because spectrum is used where people are. If you go to remote areas where farms are, the spectrum is lying fallow. And we need to use dynamic spectrum access techniques in other parts of the spectrum, which are there but not being used. And the FCC is also taking steps in that direction to enable more dynamic spectrum access. But that said, I think we need to keep thinking of new ways. I'm sure at some point we'll run into this bandwidth bottleneck. With TV spectrum, I'm assuming, or in rural areas, it will take more time to get filled, but it will get there. And we'll have to keep innovating of new ways to provide connectivity. At Microsoft itself, we are looking at private 5G as a possible way to do it, looking at space communications. We launched a product last year called Azure for Space, which is around all the different things we're doing in the space domain. So there are different ways in which we have to address it. TV white spaces, if we could think of it as one tool, but we need to keep looking at more.
Ranveer, I'll just take one last question, and I will not put the questions that came after 4 p.m. The question is, what challenges do you think will be need to solve in order for the data collected from smartphones and Wi-Fi signals to become widely adopted and competitive so that people actually use it?
Yeah, no, so I think we need to do more here, right? So, with smartphones and Wi-Fi, there's some interesting challenges. Even though we have shown the first stage of what can be done with Wi-Fi signals, most of the commercial Wi-Fi chipsets don't support the CSI information on the smartphone. They don't support getting that, even though they have this information, they don't expose it to the applications. We'll have to work with the chip vendors, with the firmware makers for those phones to make these signals more easily available to applications. We've shown it on a few demo phones, but we need to take it to the next level to make it widely adopted. Maybe there will be a farmer version of the phone, a phone that is made for farmers, which exposes this information. So I think that's one. The other thing that we need to do is correlate this information with other sensors. That is, rather than thinking of it as in isolation, seeing how we can make it more easily adopted by farmers without giving up on fidelity. So that's where we're looking at multimodal sensing with Wi-Fi, with other modalities. Say you have satellite data, you might have at least one sensor in a village. Can we use that to bootstrap things? So using it in combination of other modalities of sensing in the short term. In the longer term, I think if you think of 10, 15 years, I'm assuming it will be at a point where anyone will be able to just use their phone to start doing these measurements.
Wonderful. Okay, so I also saw that Agelos, I'm not sure if this is the way I pronounce your name. He also I know he's been working on for agriculture sensing in TU Crete for a few years. He mentioned some comments. I think it'd be great if you connect directly with Ranveer.
Yeah, you have my LinkedIn connection. My email is ranveer@microsoft.com. Please do connect. I love talking to people in academia and ways in which we can, because these are hard problems. One person, one company cannot address it. We all need to come together to solve bits and pieces and help address this problem.
Great. And with this, we'll wrap up the talk. Thank you everyone for attending, and we'll see you in the next IoT. Thank you so much, Ranveer, for joining us today, for a wonderful talk, and for taking all the questions and answering them thoroughly.
Thank you, Father. Thank you, everyone. Bye.